begin by telling people what our proposition is. Okay, this is our predicate, P of n, to be more precise. But what is it that we're saying about n? What is it that we're trying to prove? The predicate is exactly what's stated here. So let P of n be, okay, the proposition that this sum, well, let me rewrite this, that 1 plus 2 plus blah, 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 plus 2 to the n, okay? So notice that these are the powers of 2, okay? So just, I know this is familiar to people, but, okay, so 2 to the 0th, 2 to the 1st, okay? The sum of the first n plus 1 powers of 2, okay, happens to be 2 to the n plus 1, exactly, plus 1 less, okay? So that's the proposition that this holds for the integer for any n, for this n. Okay, first things first. Okay, you may be familiar with this as a computer scientist, with summing the powers of 2. That you may know that when you sum up the first few consecutive powers of 2, you get the next power of 2 less 1. Okay, so but let's check. So first of all, 1 equals 2 to the 1 minus 1. So that 1 is 2 to the 0. That's this guy. That's 1 right here, which is 2 to the 0. Okay, just one term in the sum. That's the next power of 2. Okay, that's that 1 is the 0th power of 2. It's going to be the next power of 2, 2 to the 1 minus 1. Okay, that works out. That's not bad. How about 1 plus 2 to the 1st? Is that 2 to the 2nd minus 1? Yeah, that's 3, and that's 3. So that works out. Okay, let's do one more. 1 plus 2 plus 2 to the 2nd plus 2 to the 3rd. That should be 15, which is 2 to the, which is 2 to the 4th minus 1, right? So that's 16 minus 1. That's 15. On that side, I have 1 plus 2 plus 4 plus 8. That's 15. So 15 is 15. Okay, and so on. So you check the next. You'll get 31 equals 31. Then 63 equals 63. 127 equals 127. 255 is 255, and so on. Okay. Okay, so that's fine. So how do we prove this? Now, I've stated what my proposition was going to be. Here it is. That's what we want to prove. And what's the standard way of proving this? By induction. A couple of things we need to check. First, the basis step. We actually just check the basis step. The basis step is that we must show, basis step is to show that P of, well, in this case, P of 0, right? So P of 0, it says, what's the first n that I'm proving this for? P of 0 is true. Well, P of 0 is true. It is, because 2 to the 0 is 2 to the 1 minus 1. So P0 is true. Okay, so basis step is to show that P of 0 was true. It's true. Nobody argues with that. How about the inductive step? What's the inductive step? Okay, so we should probably be doing Simpson's clouds here. So help me out. So the inductive step that what you've just suggested in the very beginning of this class is pk implies p of k, okay? A pk plus 1. So here we must show that p of k for any k implies pk plus 1. Okay, so so let's assume that p of k is true. So assume pk is true. It's true. So now I'm making a Simpson's cloud here. Just a reminder for myself here. I'll erase this in a second. So what is my p of k? So p of k. Well, p of k, 1 plus 2 plus 2 to the k is 2k plus 1 minus 1. That's what p of k is true. From this, I want to conclude that 1 plus 2 plus 2 to the 2nd plus 2 to the k plus 2 to the k plus 1, okay, that was going to be p of k plus 1. P of k plus 1 is going to be 1 plus 2 plus blah, blah, blah. This is my Simpson's cloud. 2k plus 1 is 2k plus 2 minus 1, right? That's what I want to prove. Do people see this? Right? So But how do I prove this?
Shouldn't it be k plus 1 then instead of k?
Sorry, one more time.
Shouldn't that thing at the bottom like be p of k plus 1 instead
Yes,
of...
yes. Of course. P of k plus 1. P of k plus 1. That's my pk plus 1. And just to be clear that everyone sees what we mean here, is pk plus 1 minus 1. So, okay. So how do we prove this? Well, that's going to be like by the inductive hypothesis. By the inductive hypothesis, what can I claim? This is an inductive hypothesis. That the blue piece is certainly 2 to the k minus 1, to k plus 1 minus 1, right? The blue piece. Plus I have this 2k plus 1 piece. 2k plus 1 piece, right? That's this is just by the inductive hypothesis. Okay, but that is by algebra. Now this is by algebra. Algebra is this 2k plus 1 plus that 2k plus 1 and that minus 1 that came from the blue piece. But all of that is, of course, 2 times 2k plus 1 minus 1, which is the same as 2 to the k plus 2 minus 1. Okay, which is what I wanted to prove here in my Simpsons cloud. This is what I was after. That's why I put the Simpsons cloud there. Here, that was the Simpsons cloud, which I'm about to erase. So the point is that we have shown, so let me erase the Simpsons cloud here. Okay. So what have we done? We have shown, we have completed the inductive step. Okay, so we have completed the basis step, and we have completed the inductive step. Now, because of the principle of mathematical induction that you've reminded me at the very beginning, that says that if I complete the inductive step together with the basis step, I can conclude that P of n is true for all n, true for all n greater than or equal to 0, which Pn is my proposition that I started this proof to begin with. So I start with the proposition that I want to prove up there, and I conclude that this must be true by the principle of induction because I've shown both of these steps. And then I say this completes the proof. Right? I write down something like QED here, or just put a square that says this completes the proof. So any questions about this proof? This is a typical proof by induction. These are so far we've seen quite straightforward proofs. Are there any questions about this? We'll see a couple more straightforward ones. Any questions? Any questions? Okay, we'll do a couple more here. We'll do all of these. But if this is clear, let me ask you a question. Okay, now I'm going to prove that all horses are of the same color. Okay, so can I prove this by induction? Does that make sense? So let's have this sink in for just one cup for a second. Does that make sense, like what I just claimed? All horses are the same color. Does this even make sense? Okay. Or you're like most people, like what? What is he talking about? Okay, first of all, well, let's prove this. To prove something like this, first we have to rephrase this statement so that we have some variable n in there so that we can say what our Pn is and what it is that we're proving. So there's some variable that we can induct on, right? Okay, some n that we can talk about. So I'm going to rephrase this sentence here. This one. All the horses are the same color. All the horses are the same color. Into a theorem that says that for any set of horses, n horses, okay, n can be 1 horse, 2 horses, 7 horses, 57 horses, 19 million horses. All the horses are of the same color, just the same color. So let's prove this. Okay, I'm going to prove this, and you tell me if there's something I didn't quite learn when I was listening to this class on induction. So I think I've kind of understood what they were talking about. So I think I can carry out this proof. So you tell me where I'm making the mistake. The proof is by, so I'm told, I'm going by the template that I'm given at the very end of these slides that says, first tell the people that the proof is by induction. So I'm going like checking off all the boxes, like doing everything right. So, okay, so I'm going to say proof is by induction. By induction. I'm telling people that the proof is by induction. Let the inductive hypothesis be, let the inductive hypothesis be Pn. Okay. Let me just rephrase this to be clear. Okay, maybe this is it. So every set of n horses that you take, they're all of the same color. So in every set of n horses, all of them are of the same color. All of them are of the same color. Okay, sounds reasonable. Because my proof is by induction, I'm going to check the base case. So I'm checking the base case. The basis, what is that? So this is, so P, I want to prove that P of 1 is true. P of 1 is true. Well, that's trivially true because you take one horse, okay, and one horse is, there's only one horse, so it is of some color. So all the horses in that set of one horses, all of those horses are of the same color. P1 is true because the set has one horse of some color. So all horses, in other words, one horse. So all horses are the same color. Okay, I don't think people would argue with that. That's fine. We'll check the base case. Now, inductive step. Inductive step. The inductive step tells me to check that P of K implies P of K plus 1. So we need to check. So to show that P of K implies P of K plus 1, assume that P of K is true. First of all, what does that mean? So now notice P of K says in every set, so P of K, here's my Simpsons cloud. P of K says all the horses, so here's my, just to be sure, my inductive hypothesis right there, okay? So P of K, just to be clear, so this is my P of K. In every set of K horses, all of them, K horses are of the same color. Have the same color. Okay, so that's my inductive hypothesis. That's my that's my inductive hypothesis. But from this, I want to show that PK plus 1 is true. So this is my Simpsons cloud. So here's my Simpsons cloud that says PK plus 1 now. PK plus 1. Okay. PK plus 1 is going to say that in every set of K plus 1 horses now, K plus 1 horses, should have been blue maybe, K plus 1 horses, just to make sure people see this, all K plus 1 of them, all K plus 1 of them are the same color. K plus 1 of them are of the same color. Okay, so I've just written out PK and PK plus 1. I can show that PK implies PK plus 1. Here's how I'm going to show it. Here are my horses. Well, here's H1, H2. I could draw the horses, but I think for me, because I'm no Picasso, it's easier for me to show it this way. So here's my P of k, here's my H of k plus 1. I have k plus 1 horses. These guys are of the same color, by IH. Say that color is red, whatever. That's because I've used the red color. By the inductive hypothesis, I have k horses, k of them. These are k of them. So these are also k of them, starting from H2 up to k plus 1, are of the same color, are of the same color. So this implies, so this is, but assuming the inductive, this implies that all of them are of the same color. All H1, HK plus 1 are of the same color. Okay, just to be clear, so let's say color of H1, right, equals color of H2 by the inductive hypothesis, and color of H2, okay, so let's write it more clearly, just to be sure. Color H2, H3, blah, 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 HK, and color H2, blah, 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 HK. Is the color of HK plus 1, also by the inductive hypothesis. So H1, color of H1 is color HK plus 1. So all horses are of the same color here. This is like, just to write it out explicitly. I mean, you can see it from the picture here just as well. This picture here, that all k plus 1 of them have to be of the same color. Okay, so I've concluded here in my inductive step. I don't think anyone can argue with this argument. Okay. Okay, so we've shown, therefore, so let's say proof below. Therefore, and that's my proof. I'm concluding, I'm writing the last sentence of my proof. Therefore, by the principle of math induction, Pn is true. Is true. That is, all horses are of the same color. Okay, so that's my proof. This is what I learned in class. I'm taking this course in discrete math. So I'm covering this topic of induction. I went to class. I sort of understood this. I think I understand it. So can anyone help me out? I'm kind of lost. I mean, I did all of it. I mean, this is homework assignment. I'm given this template. Okay, so I'm just doing what they told me to do and submitting this, and I'm getting 0 points. What's wrong? Okay, looks like I did my part. Somehow, what am I missing?
I had a question. So
yeah,
that I didn't understand. So how do we know that from H2 to HK all of them are of the same color though? Because
this piece by the inductive. So here's my every set of k horses. Is this a set of k horses? Do I have k horses here?
Yeah, but
yeah, I've just numbered H. These numbers are what I gave these horses. I mean, these horses are out there in the meadows playing. I just numbered them. The numbers I've assigned, I've put them in an array, indexed collection of some sort. These are indices that I gave to the horses. The horses don't care what indices I give them. Okay, but do you agree that there are k horses here?
Yeah, but then we can just always prove that they're of the same color, right? Because we can just always.
We're not proving that k horses in this inductive. This is the whole point of understanding induction. We're not assuming that all k horses are of the same color. We're saying that if we assume that that's what we're trying to prove, that all k for any k, if we used n there for that reason to distinguish this k from that n, just the different variable name, to make sure that it's just to underline that these are different claims. Here we're claiming that if we assumed that k horses, all k horses, if we assume p, so here's what we're trying to prove. implication, right? If we assume PK, this must follow. That's how the implication is going to be proven to be true. So let's assume that all K horses are of the same color. That's what this is saying. If we assume, so this is saying, if we assume that every K horses you take in the world, every set of K horses you take, all of them will be of the same color, right? Are these K horses? Do I have K horses? I've given them the indices, but do you agree that I have K horses here?
Yeah.
Okay. Do I have K horses here?
Yep.
Okay. Do I have K plus 1 horses total with this overlap?
Yep.
Okay. So because these are of the same color and these are of the same color, and this guy is the same color as any one of these, it must be the same, and because this is of the same color as any one of these, this is the same color as these, and the same color as these. So K plus 1 horses have to be of the same color. I mean, what's wrong with this? This is true. This is true. I mean, so if we assume that all cases are of the same color, then all K plus 1 horses will be of the same color. So what am I missing? What am I missing? Somehow, I'm told to use this template, and I'm doing what I'm told. Somehow there's something wrong. All right, so please help me out. Like, we have to move on, do a couple more examples today. We're wrapping up this chapter and start an induction. I want to do a couple more examples. So we'll want to get over this pesky issue here. I mean, or should we leave this aside and come back to it in the last few minutes of the class?
I was going to say something. I don't know if it's right.
Yeah, no. Okay, so you should say it because it's not the way we operate, right? It's
okay. So, I mean, I was just looking at prior examples, and I feel like when you introduced the topic to us, we kind of, obviously we did most of the examples with like integers themselves, but I feel like the infinite like rung or like the domino effect doesn't really apply here because there's a lot of like inference and implication here that you're just going to assume that the next horse is going to be the same color. No. I don't know if that's allowed.
What do you mean next horse is going to be the same? The domino effect, I think, applies exactly here.
Okay.
Where am I assuming that the next horse is going to be? I'm not assuming that at all. Did I assume anywhere that the next horse, the next domino will fall over? I assume that's factored in here slightly differently. What do you mean the next horse is going to be of the same color? Well, yes. If K, any K, if K is like 7, okay, let's say this K is 7. I see a horse, okay? It's not about the next horse. Any 7, well, including the next one, any 7 horses I take, they're going to be of the same color. That's my P of K. Is this a valid proposition? Is this a sentence that evaluates either true or false when K is 7? Any set of 7 horses is of the same color. That's something, they are of the same color. That's something that's either true or false, right? Do people agree? Okay. So that's a proposition. Every set of 7 horses, so I see 7, okay, so you say, I see 2 horses, okay, fine. You're saying something about the next horse. Let's draw 1 horse, okay? I don't know how to draw a horse. Let me just, okay. So 1 horse and another horse. Say I have 2 horses. Next horse, so 2 horses. They're of the same color. Then I see another 2 horses, okay? They are of the same color, maybe. No overlap. Another 2 horses, no overlap. But using that, I can't prove. If I see a horse, the next horse, okay, you say the next horse. Here's the third. 1, 2, 3. Again, the numbering is what I give to the horses. Here's my set of 2 horses. Here's my set of 2 horses. That is my inductive hypothesis. Every set of 2 horses have the same color here. So these, because every set of 2 horses has have the same color, every set of 3 now have to have the same color. Right? I mean, there's no doubt that that is happening. But I'm still, there's something wrong. There's clearly, man, it's so hard to see this bug in this proof.
Is it because you can't show that it's true for only 2 horses?
That's it.
There's no smaller set of more than 1 horse to compare it to.
Here's what I missed. That's exactly right. That is exactly right. Does this apply? Okay, so I've proved that P2 implies P3 here with this picture. P2 implies P3, I've shown. Same way I can show that P3 implies P4. Here's the knockoff dominoes. Somebody mentioned dominoes, right? Here's the knockoff effect of the dominoes. I've proven this. I've proven this. Here's the knockoff effect, and then knock effect of the dominoes. P5. All of this I've shown. Here I've shown that PK implies PK plus 1. This is all true. This is all true. But what I haven't shown is that P1 implies P2. If every, so you have these horses. So you have one horse, you have another horse. It's certainly true that every set of one horses, if you can say it that way, and every set of one horse is of the same color. But when I make this implication here, does P1 imply P2? No, because I can't have an overlap. This set here of horses, which I'm relying on for the overlap, that set is empty. That's an empty set. And now if you go back to the previous lecture, when I began by talking the dangerous dots, I mentioned it a few times, and people were, well, why is he talking about like danger? What do you mean dangerous? Well, here's the danger of it. In these dots, I'm assuming that there is something present, but there is nothing there in those dots. That was an empty set. So I can't make this claim. So the domino effect breaks down at this stage. At this stage where I cannot make this implication, P1 implies P2. That's the problem of the domino effect. Okay. All right, does that make sense? So you kind of have, this is, you know, that's, you have to be careful when carrying out inductive proofs. Okay.
Another question, we can't prove just because you couldn't, that the implication P of 1 implies P of 2 was, we could not prove that part, right?
Yes, exactly. The whole induction breaks down. It's a bogus proof because I can't apply the principle of mathematical induction. Because when I was writing this down, right, when I was writing the proof of the inductive step, I assumed here that there was something in the middle. Okay, like I was implicitly assuming that k is greater than 2, and you should have caught me there. You know, my argument, the inductive step, should work for every k. I'm proving it for any k. For in every set of k horses, this is my assumption. In every set of k plus 1 horses, that should be my conclusion, right? Do people see this? It's so hard to catch this proof, right? Okay.
All right. Why does P1 not imply P2?
Okay. So let's see. Here's why it does not imply P2. Here's why it does not imply P2. Okay, this is my P. What is my P2 and what is my P1? Let me leave that there. P1. What is P1? What is P2? So help me out. Let's answer your question. What is P1?
P1 is the initial red horse.
Right. No, there's no initial. Every set of one. So notice what the statement is. Let's think of it as an English sentence. Okay, I guess initial would be justified if we're thinking in terms of domino. Okay, fine, the initial. But can I say that every set of one horse has the same color? Awkward English sentence, I agree. But you see a horse, it has some color. So every set of one horse, let's put this in quotation marks, because as an English sentence, you wouldn't say it, but it makes sense. It semantically is correct. Every set of one horse has the same color. Do you agree?
Yeah.
What's P2? Every set of 2 horses has the same color. Again, yes, set has the color. I mean, in every set, it's a better English sentence to say in every set of 2 horses, both are of the same color. Are of the same color. Do you agree?
Yep.
Now, your question is, why does P1 not imply P2? And my answer to this is, why should it? Well, I've proved to you why P2 would imply P3. That I've proven to you by drawing these horses here. 1 horse, 2 horse, 3 horse, 2 of the same color, 2 of the same color, therefore 3 of the same color. Okay, that I've proven to you. But why? So the better question is, why could it possibly follow that if each horse has some color? Why should it be the same? Okay, so here's the white horse. Here's the brown horse. Okay, it's true. Every single horse has some color. P1. Is it true that they have the same color? Counterexample proof. That's why it's not true. Does that make sense why it's not true?
Yeah.
It's a counterexample. So that's why it's not true. But now notice that if my base case were different, imagine a universe. Okay, so if I started with 2 cases. Now, if it's, by the way, if I start by the base case of 2, if it's true that every set of 2 horses, both are of the same color, in every set of 2 horses, both have the same color, then yes, it is true that any set of n horses will have the same color. Then you can use this proof by induction if you start at 2. But of course, the universe in which we live, it is not the case that every set of 2 horses have the same color. Okay, does that make sense now? Does this make sense now? So you kind of have to be careful with the proofs by induction, right? Any other remarks before we move on? A couple of things.
We couldn't do that overlapping technique that we did before, right?
Yes. Yeah, that's the point. That overlapping technique worked with 3 horses or more.
Oh, nice. Okay.
Yeah, so it didn't work with these 2 horses here. P1 implies P2. That didn't work here.
So most like problems with induction that we have to be careful. Are these for like the base, how the basic step connects to the rest of the problem, or can
yeah? So in this case, if my basis step were different, if my basis step started at 2, that's why I need to check the basis step always. If my basis step started at 2, then I could certainly conclude this. This conclusion would be true. If my base for any set of 2 horses, if n greater that all horses are of the same color, that you can prove by induction if you start at 2. But that assumes that the base case assumes that any set of 2 horses have the same color. Then yeah. So if you change this to this, then this is a true theorem. But the assumption, the basis case would be false in the real world. But in an imagined world where every 2 horses have the same color, that every set of any k horses will have the same color. That's true. Okay, let's practice a little bit more. Let's prove an inequality today. Okay, we did that one. Okay, now you help me out. So let me be a little bit short now. What is my P of n? So I'm proving this. I'm going to do a couple more examples at least. I want to show that inequalities can also be proven by induction. Okay, so what is my P of n here?
n is less than 2 to the n?
Yes. N is less than exactly same as what we're trying to for n greater than 0. So let's say n is greater than or equal to 1. Let's start. Okay, that's my P of n. Basis step. Okay, P of 1, is it true? Well, 1 is less than 2 to the 1, okay, which equals 1. So that checks out. Inductive step. P of k is true. Want to show that pk plus 1 is true. So let's skip the Simpsons cloud this time. Maybe we can do it. What is pk plus 1? So you want to show that k plus 1 is less, and here's the Simpsons cloud, is going to be less than 2k plus 1. That's what I want to show in the end. But I'm starting by the inductive hypothesis. So let me use different colors just so I have my k plus 1. Here's my k plus 1. By the inductive hypothesis, k is less than 2 to the k. And plus 1, I'm just carrying over. And I'm going to say that this is by the inductive hypothesis. This is true. Do people agree? I think people agree. But can I also say that this is less than 2 to the k? Well, okay, can I say this? Plus 2 to the k. Can I say that 1 is smaller than 2 to the k by algebra? Because 1 is smaller than 2 to the k, right? 1 is just 1, and 2 to the k is an increasing function. Okay, so if 1 is smaller than 2 to the first, it's going to be smaller than 2 to the second, 2 to the 7th, 2 to the 15th, so on. So that is that. But that is equal 2 times 2 to the k, which is 2 to the k plus 1. So we've shown that P of k implies pk plus 1. So that's my pk plus 1. This is what I wanted to show. That's my pk plus 1, that k plus 1 was smaller than 2 to the k plus 1. Therefore, by the principle, blah, 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 by induction, Pn is true. It's true for all n. Okay, completes the proof. Okay, let's see if we can knock another one out. Okay, I'll let you prove this yourself. Okay, so let's prove that because this one has a different case, different base case. Again, P of n. Okay, I'm gonna use a different color so that we don't confuse it with the previous part. P of n is gonna be this. This is my P of n. Okay, base case. 2 to the 1 is less than or equal 1. Oops. Where did I miss? What did I do wrong? It's not less than that. 2 to the 2 is less than or equal to, oops, I guess exclamation point. Is 2 to the 3 less than or equal, okay, this should say 2 factorial, which is 2. 3 factorial, which is 6. Again, this is 8. This is, oops. So that it isn't, none of these are true. These are all oopses. So you start with the base case, So I'm going to erase all of this. This was scratch work. Then I pay attention to this. Oh, when base case, n is 4. Must show that P of 4, and maybe we should use K here, but that doesn't matter. It won't be. P4 is true. But it is. P of 4 says 2 to the 4 is less than 4 factorial. 4. Okay, that's what it says, not 4. You already plugged K in there. Is that true?
Yeah.
Okay, this is 16 less than 24. So that checks out. That's check mark. Okay, not part of the proof. Okay, so inductive step. So now you help me out. What am I writing down? So I want to show pk plus 1 is true whenever, just another way of phrasing that I'm proving the implication, whenever pk is true. Just for variety, we'll phrase it differently. So I can assume pk is true, and I want to prove pk plus 1. What is pk plus 1? Help me write down. I want to prove what's my end of the Simpsons cloud. What should be my end result that I'm after? Can anyone help me out?
K plus 1 factorial.
Yeah, yes, exactly. K plus 1 factorial. That's what I want to prove. Okay, so let's start. 2k plus 1. What do I do? I'm kind of lost. You help me out because I'm lost. How do I show this? I want to get to k plus 1 factorial. Can I write this down as 2 times, how should I write this down? 2 to the k times 2, let's say. First of all, that's not true, what I've just written. Is that true?
Yeah.
Now, is it true that this okay, let's put it this way. That's that. Now, is it true that this is smaller than k factorial times 2? Is that true? By inductive hypothesis. And here,
Yes.
okay, because this is my 2 of k, and this is my k factorial. That's my inductive hypothesis, P of k, in green. P of k is 2k, is less than k factorial. So that's true. People agree. Then, is it true that this is less than k factorial? Now I want to get to k plus 1 factorial. So is 2 smaller than k plus 1?
Yes.
Yeah.
Because 2 is smaller than k plus 1. Because I'm taking for k greater than or equal 4. As long as k is greater than or equal 4, it doesn't even have to, it can be smaller, like k starting from 3, but k greater than 4, this is true. So, but is it true that this is k plus 1 factorial then? Right?
Yeah.
So here's my Simpson's end result. So this is what I got. This completes the inductive step. This completes the inductive step, which is what we wanted to show. Let's knock out 2 more. Any questions about this? Now, anybody help me with this one? Like before we leave, I want to knock out 2 more of these. Okay, and then we'll skip the Bill in the center. So we're going to skip the one that says like Bill's statue in the center. That example from the book. It's also in the slides. We're going to skip that one. But we definitely need to do these 2. All right, so my P of K inductive hypothesis is going to be N, okay, I wrote K, okay, fine. Inductive hypothesis, I'm going to write down. So again, I'm being loose here. Now you have the template. So when you write it up, do it by the template as I did in all the previous examples. Here I'm doing scratch work. My inductive hypothesis is P of K is that K cubed minus K is a multiple of 3. That's my inductive hypothesis. Well, it's divisible by 3, okay, of 3. Okay, for any K, okay? That's my inductive hypothesis. Base case. PE0 is that 0 cubed minus 0 is 3 times 0. True. So base case checks out. Inductive step. I could have started at 1 just to be sure, but that's okay. Inductive step. Oh, is it positive? Yeah, I should have started at 1. Okay, then I'm wrong, kind of, although it's true for 0, but let's just prove what we're asked to prove. 1 cubed minus 1 is 3 times 0 still. So P1 is true. Okay, that's what we were asked to prove. Okay, inductive step. Well, what does the inductive step say? The inductive step says that PK, so that's what I'm trying to prove. PK implies PK plus 1. That's what I want to prove by the principle of induction. Then my inductive hypothesis will be true for any K. So, okay, so assume PK is true. Assume PK. So this is what we get to assume. So PK plus 1 then is what I'm working with. What is PK plus 1? K plus 1 cubed minus K plus 1. I want to show that this is a multiple of 3. This is my end result. Multiple of 3, multiple of 3. That's what I want to prove. So let's keep these colors here. It would be clearer. Okay, so, well, let's just expand this. This is going to be K cubed plus 3K squared plus 3K times 1 squared, 3K plus 1 minus K minus 1, okay? Then I'm going to cancel something. These 1s go out. What do I get? This one is equal, so this one is equal K cubed plus 3K squared plus 3K. Well, I want to show that this is divisible by 3. Is this divisible by 3? And it beats me. I don't know. Yes.
Isn't it 2K though, because you subtract by K?
Oh, yeah, I'm sorry. Yes. Yeah, that's correct. That is correct. All right, yeah. Is this divisible by 3? Okay, so is this divisible by 3? I mean, I don't know. It beats me. I mean, do people see? Maybe somebody sees that this is divisible by 3. I don't.
You can subtract 1K and put it with the K cubed.
Oh, that's
and then the 2K become a 3K to compensate for that.
Oh, I think that's an excellent idea. So help me out. Like I'm still missing it. I heard some. So you said, so here's my PK is right there. So you're saying this is nice. So you're saying, let me use a different color. I think this. You tell me if that's not what you're saying, but I think I got you correctly. So you're saying that this K cubed here, subtract 1K here, okay, and then add that k so that the equality is not compromised in any way, but 2k plus k. And then this 3k squared, I'm going to leave the way it is. I'm doing nothing about it. It's going to be k cubed minus k right here. And this one is going to be 3 times, well, what's something inside? K squared plus k. Do people see this? Do people see how this was a good idea? Because the second piece, this is multiple of 3. And this is by, now I get to use, by the inductive hypothesis, is a multiple of 3. This one was by algebra. And this one is a multiple of 3 by the inductive hypothesis. That is. Do people see this? Okay, do people see this?
Shouldn't it be k inside the parentheses of 3, k cubed plus minus k though? Because this is what, didn't we say that initially, that k cubed minus k for the p of k is equal to 3 times k cubed minus k, right?
No, 3 k cubed, we said the k cubed minus k is like 3 times some d, is a multiple of 3. Here's our claim. P of k is that this is a multiple of 3. So that equals some 3 times some, it's divisible by 3. That's what we're claiming. So here, all right, so are we on the same page with all of this? This is kind of a little bit more challenging because it's, you can get lucky and get this insight like the one you got here of adding and subtracting k. That was nice, right? Maybe, okay, so let's see what this is like. So I think we need some insight there as well. And maybe you can help me. So let me, first of all, base case. So I'm going to skip a bunch of parts. So this is going to be my P of n. This is what I'm trying to prove, that it's divisible by 57 for all of these n's. Base case, okay, is, well, P of 0, again, they want me to start at P n 0. That's even better because 7, so this is going to be 7 to the 0 plus 2 plus 8 to the 2 times 0 plus 1 is divisible by 57. Well, this is, okay, so plus. This is going to be, the first piece is 49, that's 7 squared. And this piece is 8, and that's exactly 57, which is divisible by 57. It's a multiple of 57, so that's good. So base case checks out. So you plug in k equals 0, and we're good to go. Inductive step. So in the inductive step, assume P of k. So let's write down pk plus 1. This is what I want to get, pk plus 1. I'm starting. So this is going to be 7 to the power of k plus 1 plus 2. I'm plugging in k plus 1 for n here. Plus 8 times 2, k plus 1 plus 1. I must show at the end, here's blah, 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 I'm going to say, and I want to end up by saying that is divisible by 57. That's what I want to conclude at the end of the day, that this is divisible by 57. Okay, and I get to use the inductive hypothesis. Get to use the inductive hypothesis. That is the fact that 7 to the k plus 2 plus, oh, this is, why did I write 2 here? Isn't that 8? Yeah. The 7 to the k plus 2 plus 8 to the k plus 1 is indeed divisible by 57. Okay, so I get to use this fact, but I want to conclude this fact after I do whatever I'll do. So let me rewrite, first of all, because I get to use the inductive hypothesis, this one. I want to isolate pieces. So do you agree that this is going to be 7 to the k? Do you agree that this is the same as that? The first piece. And do you agree that this is the same as 2k plus 1 plus 6 times 64? Do you agree?
Yep.
Right, by algebra. Okay, now, oh, okay. Okay, so can people help me out? Interesting. Okay, so what can people, this is this is kind of either you can see or you can't see. Okay, this is kind of, all right, so yeah.
You can split 64 into 57.
Yeah, yeah, that, you see that? So 64, do you see that 64 is 57 plus 7, right? And this is 7. Now let me use the red ones here. 8, 2k plus 1. And here is 7k plus 1, k plus 2, plus. So here's what we have. You end up with 7 times 7k plus 2 plus 8, 2k plus 1, plus, let me erase this, like Simpson's cloud, we know what we're proving. And then you have 57 times, okay, these colors, 57 times, whatever, 8 to the k plus 1. And again, we get the same result. Is a multiple of 57 by algebra. And this is a multiple of 57 by the inductive hypothesis, right? Because this is 7 times something that's multiple of 57, because here's my inductive hypothesis. That's why I should write it down. But anyway, plugging k here, this is a multiple of 57. Therefore, this is a multiple of 57 here. So you get something like 7 times, like 57 times some d, right? So this is a multiple of 57. This is a multiple of 57 because it's 57 times something. So their sum is a multiple of 57. And that concludes the proof.